Hello, good afternoon, good morning, good evening, wherever you are around the world. My name is Nick Rendell with Technical Toolboxes, and today we have two speakers, David Willoughby, who's a longtime expert in HDD and AC mitigation, and Gary Hines of the Pipeline Research Council. Just kind of a couple housekeeping notes before we dive into the content. If you do have questions throughout the webcast, there is a question pane on the right-hand side. Go ahead and enter your question into the question pane, and at the end, there will be ample time for discussion and questions there. So with that, I'm going to go through the agenda briefly, and from there, we will hand it over to Gary and David. Next slide. So just quick overview of the agenda today. So we're just going to kind of look at technical toolboxes and the Pipeline PRCI, the Pipeline Research Council International, kind of our relationship there and how we translate research into software. And then we're going to dive into the meat of this presentation and really look at the process of AC interference modeling and the steps that David recommends there. And finally, we'll look at briefly how we achieve this modeling with software and make it kind of operationalized within your organization. At the end, we will have plenty of time for Q&A, like I said, so please ask those questions in the question pane. With that, I will hand it over to Gary. Thank you.
All right, Nick, thank you. And as Nick mentioned, Gary Hines with Pipeline Research Council International, PRCI. I have the unique privilege within our organization of working with technical toolboxes. Primary responsibility with that is transferring our intellectual property, our IP, into something that's usable, something that's functional, something that's operational. And we're going to talk about one of those products today. So I do want to give some background about PRCI for those that may not know about the organization, but I want to quickly allow for the transition to David to go through the content, what I would call the meat of this webinar. For those that are not familiar with our organization, just as the name implies, Pipeline Research Council International, as you probably saw in the mission statement previously, we certainly work in a collaborative way I'll emphasize a few words within that mission statement, is the application of research. So again, this is a great example today of how that's been done historically within the organization. Certainly you'll see there from a membership perspective, we are a not-for-profit trade association, and so you'll see in the list there that we have a wide range of pipelines that actually belong to us as members that carry biofuels, natural gas, crude, refined products, etc. And again, on the research side, there's a lot that's learned through the development of the research, but most importantly, as we'll see here, on the deployment and technical transfer of that information to the industry. Again, from a council perspective, the name implies peer-based, peer-reviewed. So this is industry content. It's not just from one operator, one vendor, one consultant, one service provider. We bring together the industry for that peer review and again, industry-driven research for the output. And lastly, we are international. I'll cover this on the next slide a bit. But we do have membership that covers the Asian area, certainly Australia, Europe, Middle East, and North America. So on this next slide, you'll see really just a diversity of who our membership includes. And again, we are, from a count perspective, we are heavily weighted on the North American pipeline operators. 45 of those reside in North America. But again, we do have, I would say, a really good representation around the world, that 25 non-North American operators that's also within our membership. So proud to state that as well. Again, within that membership breakdown, we do have natural gas, liquid operators, and then a good number that have a combination of assets as well. Also within our membership, we do have other trade associations. You'll see those listed there. Some of those recognizable, I'm sure. And probably what's not known as well within our organization is that whenever you look at the split in membership, it is a pretty even balance between the pipeline operators and what we call our associate members, more specifically in a lot of our technical committees is our technical program associate members. And again, those are around the world as well. So it's about an even split between membership whenever we look at count. Moving more specifically on the next slide into how does this work? I won't read this word for word, but essentially that bottom graphic there on the slide, I think really represents this, that we identify a challenge, there's an idea of something that needs to be solved. PRCI members come together and they fund that. They allocate their funds to a project, and the key word that we use there is leverage. So as a simple example, if there is a project that requires $100,000 of research funding needed, and if there's 10 members that want to actually fund that work, then they only spend $10,000, and so they get a 10-to-1 leverage associated with the output. And then once that work is funded, then we actually execute. That's what PRCI does, is we manage the research portfolio, and we help the members execute that. We do not ourselves directly do research work. We hire research contractors to actually do that work. And then once that's finished, again, in the case today, is the development of a solution. And then where we partner with Technical Toolboxes, you'll see there on the last two icons is the integration, looking to add value, and as I said earlier, more operationalize a research solution to something that is usable for the industry, and then of course leveraging Technical Toolboxes to take this to market and get it applied more broadly than just within our membership. So that's really the background that I wanted to give regarding our partnership with Technical Toolboxes, where the research comes in, peer reviewed, peer evaluated, and then published. And then again, that partnering effort to actually work with Technical Toolboxes as a partner. So I'll be around to certainly help with any questions. I suspect a lot of them will be technical in nature. But with that, David, I'll turn it over to you to give a self-introduction and actually get into the technical meat of this webinar today.
Thank you, Gary, and thank you, Nick. I'd like to welcome everyone to the webinar. Again, there's a key thing. This is going to be an introduction to AC interference on pipelines and modeling. And less than an hour introduction, of course, is as far as we can go. But I'm going to try to introduce some of the basic phenomena with AC interference. If you're not familiar with it, and how we go about trying to analyze it, and how we'll go through the process of modeling it and try to identify the level of interference that we have. Just a little bit about myself here. I've been doing this for a long time. I'm currently retired from working. I still teach classes for Technical Toolbox on a regular basis, but I retired back in 2018 from RK&K. I've been doing AC interference work since the mid 70s is when I started doing it. So I've got a good bit of experience with it. So I try to pass some of that experience on to you. I do give you my contact information there. I get telephone calls or texts or emails daily from students at various Technical Toolbox classes that they take. So again, that's how you reach out to me if you have any questions you want to ask me later on. Okay. And again, during this webinar, you have the opportunity to write in questions. Feel free to write them in, and at the end of the webinar, we'll answer as many as we have time to answer your specific questions. Now, I teach a lot of classes on AC interference, anything from webinars to 2-day in-person classes. So, we've been doing this since about 2005 when we first started teaching the AC classes, and we started doing the webinars right during COVID, when people wanted to quit doing face-to-face training. And so we've done enough of them. I kind of get a good feel on what people are still looking for and asking. And one of the things that comes to a lot of people's mind on AC interference is just understanding the actual phenomena of AC and how that causes interference on our pipelines. I'm going to cover the very basics of it this morning. We certainly can't get to it in detail, but I'll cover all the base steps with you. Now, we call electromagnetic interference, AC interference, same thing, and that's caused by the magnetic fields in both our transmission and our distribution power lines. And pay attention to that right there. When a few years back, we pretty much just paid attention to transmission lines, the high voltage lines. We didn't worry much about distribution. The past couple of decades, we found out that distribution lines can cause problems too, especially if you run parallel for a long distance. So pay attention to that today, and remember, if you have any pipelines out there, it's not just transmission lines. You can have problems with distribution lines as well. But these power lines, when they parallel with your pipelines, your buried pipelines, they can cause problems. And again, we first started seeing this back in the 60s when we first started seeing much of it, and that's grown. It keeps growing because of the increase in the energy load requirements. The power corridors are throwing more and more current down there to meet the demand, right? And so as they throw more current down there, that increases the level of interference on there. Another thing that's made us recognize it more is improvements in our coding technology. Back in the 60s, 70s, 80s, when we first started looking at this, most of the coatings on our pipe weren't that good. And a poorly coated pipe is a good AC ground. So if you have an older pipe with poor coating, you won't see as much of an AC interference problem as you will with a well-coated pipeline. So as they started getting better coatings, the coating technology got better, the AC interference problem got worse. Okay, so that's one thing that made it worse. Another thing is the tendency to locate in the right-of-ways more often. Now it's very common to share corridors and lay the pipelines and the power lines in the same right-of-way. So all that's led to an increased problem. The problem's always been there. It's just getting a little bit worse and a little bit more identified. Now, why do we worry about this? Now, it causes a series of problems on your pipeline systems. The first and foremost we have to worry about is the safety issues. And if you pick up AC voltage or current on a pipeline, anybody who might be in the vicinity of that pipeline, that they can be exposed to safety hazards, and by either touching like a test station or above ground valve or above ground metering station, anything that's above ground they can touch. And you can see right here, if they can touch it and they're standing on the ground, you have a different potential. That pipeline can be a different potential than the ground they're standing on. And of course, it's not the voltage, it's the current that's going to pass through that person's body that can cause safety issues. You can also have problem with step potentials when you're walking across the ground. And if you're working across across a valve and you have a different potential on either side of the valve, you can have problems with that as well. So first and foremost is those safety issues. So when we do our analysis and our modeling, that's one of the first things we look at to make sure that our pipeline is not going to harm. And by the way, it's not just our personnel. It could be a child out there playing in the corridor. It could be anybody out there that might touch something. So we pay close attention to those safety issues. The other side of it is what we call integrity issues. And the integrity issue can be AC corrosion. It can be your pipeline damage during faults, both power line faults or lightning faults, and also coating damage during those fault conditions. And we're not going to talk any about AC corrosion and stuff today. We don't have time in our block, but very significant that you'll see AC corrosion is pretty much a steady state induced phenomena. And this right here is what it'll look like a lot of time when you first dig it up out of the ground. That buildup is actually the byproduct, and mainly it's hardened soil. It's the byproducts in the soil that'll build a mound around that. This right here is the same one. This is what it looks like when it was cleaned up. And when they're cleaned up, they'll normally be shiny like that, hemispherical, and pretty easy to recognize a lot of time your AC corrosion. This right here was actually from a line to ground fault and a conductive interference. We'll talk about conductive in just a minute, and that's the result of that. So two major issues: safety issues, which is always first and foremost, and then the next is our pipeline integrity issues. So when we share a right of way, if your pipeline runs through a right of way with power lines, and again, it could be the high voltage transmission, it could be some of your distribution lines if you run parallel with them for a long enough way. But when you do them, you're subject to three levels of or three types of interference. You got capacitive, inductive, and conductive. And we'll talk about each of those here in just a minute. But I want you to focus on one word right here. I got there subject. If your pipeline is buried in a corridor and you're running, like here with those facilities, that you have AC interference. Because anytime you've got those electric lines, you've got magnetic fields. If you have those magnetic fields, you're picking up electromagnetic interference. What you don't know is what's the magnitude of that. How high is that level of interference? That's where the modeling and the analysis comes in to help you identify, okay, I do have it, but is it problematic or is it not problematic? Okay. So first, we're going to talk about each of these three types of interference and just give a very quick rundown on those if you haven't been exposed to them before. The first one I want to talk about is the capacitive. It's also called electrostatic. Okay, a very common term for it. Now, this is the kind of interference that only happens during construction or during maintenance activities. It's when you've got a welded pipeline put together and you've got it elevated above the ground. So it could be on rollers if you're doing pipeline construction above ground. If you dig up a trench and you've got 1,000 feet of pipe exposed in a trench, and you're just not touching the ground, you can pick it up there. Anytime you have an airspace below the pipeline, and you've got an airspace between the pipeline and your above ground power lines, you have potential for that capacitive interference. Because basically what that becomes, it becomes a capacitor, is what it is. You have the ground is a conducting plate, that the pipeline's a conducting plate, and the wire, and they'll build up that static charge. Okay. Now, the thing about these, again, they're only during construction, only during when the pipe's in maintenance, and they're caused by the induced current, which we'll talk about in a minute. And they're very short-lived. As soon as you lay that pipe in the soil, or as soon as you ground that pipe out, it's going to drain that electrostatic off. So if I took this pipe right here and I put a clamp there and I went to a grounding rod, that would drain every bit of that electrostatic off. Okay. Electrostatic is not the kind of a shock that's going to harm somebody directly. What we call that is called a nuisance shock. It's enough of a shock that somebody to feel it and make them jump or react, but not hurt them. So we're more worried about the forklift operator has a shock, and so he jumps up and runs over the guy beside him because he reacted to that mild shock. Or something I have seen, a welding operator out there welding, and you get an electrostatic shock and jumps up and sticks a welding rod in somebody else's eye. So that's the kind of problem that you have from the electrostatic. Now, conductive is the ones that happens during our line to ground faults. When something on the power line goes bad, that's what a fault is. So a tree limb could fall on the wire, the power line. One of the insulators could short out. Anything that shorts that circuit out is called a fault, a line to ground fault. So that means the current can now go from that line through the tower into the earth. Okay. Now, the current that goes from the tower into the earth right there, that is the conductive interference. Okay. Now it's called conductive because that current is transmitted by being in physical contact between the current coming out the tower footing and the pipe, and the medium it travels through, of course, is the soil. In this case, right here. So conductive is the only one that's transferred through that physical contact, through that medium. Your electrostatic and your induced, they're not. They're all transported in that magnetic field. Okay, so that's why we call it conductive, and it's that current when you have a fault, it goes down through the tower, going to the earth, and that'll go to your pipeline. Okay, now when we have a fault, and we'll pick up a lot of current. All that current's got to get back to a source like any other current, and that current's going to take every available path. And normally what it'll have the phase wires, it'll have shield wires, of course it'll have the earth, and it'll have your pipeline. And so when we model it, what we try to figure out how much of that current is going to try to get back to the source through our pipeline, and that's how we will model the level of interference that can cause both safety and pipeline interference problems. So that's conductive. That happens during a fault. The most dominant mechanism, we'll call it coupling mechanism, is our inductive or our electromagnetic. Okay. Now that's what happens under normal power line conditions. The power line's out there operating as it's designed to. You always have that magnetic field out there, and if your pipeline is within that field, then you're going to have what we call induced or inductive coupling between that power line and your pipeline. Now, a lot of things go into this. You kind of see in the diagram up here, the distance, the height. If you look at this last bullet down here, the big things that affect the level of interference we're going to have is the current. Now pay attention to that. I've got current underlined there. The voltage of the power line is not what drives the level of interference. It's the current going through that line. So you know, when we look at the power lines, we're really looking more at how much current's going through there than we're worried about voltage. Now, when I'm worried about conductive, you know, or electrostatic, the voltage takes a play. But for the induced, it's pretty much the current. The other thing is what we call circuit imbalance. If you look at these wires right here, you have three wires in our power lines. That's called a circuit. Each of those wires is called a phase wire. Okay, so you have three phase wires, and the three make up a circuit. Now, if those circuits are perfectly balanced, then they would cancel each other out, and you wouldn't have any interference at all on your pipeline. But when they get imbalanced, what that means by imbalance means that one wire is flowing more current than another wire. Okay? That's what we mean when we say imbalance. So if the circuit gets imbalanced, that's going to increase the level of induced interference you're going to have on your pipeline. The other thing is the distance between the phase wires themselves. If you go out in the corridor and you look at these phase wires, the farther apart these wires are from each other, the higher your level of interference is going to be. The closer they are together, the lower your level of interference is going to be. So it helps you, something to look at when you're out there in the field, you kind of get an idea. But another big thing is the distance between the power line and the pipeline, as you see right here, that distance right there. The farther away the pipeline is from the power lines, the lower the level of interference. The closer the pipeline is to the power line, the higher that level of interference, okay? And this right here, just to add one of the PRCI model, and you see that's a graph right there of a level of interference. Now this one here goes about 32 kilometers, is what this one went. So you can see as high as about 180 volts right here on either side. And of course you got zero down here in the middle. But we're going to look at the how we model some of this stuff in a little bit, but that's kind of what we're looking to do. But all these things right here are going to affect that. The current going through the wires, that's a big one. Any circuit imbalance we might have, that's going to have a big impact. The distance between the phase wires themselves, and of course the distance between the pipeline and the thing. Now, remember that when we're in that magnetic field, what we're really doing is inducing an AC current. We're picking up an AC current on your pipeline, and that current's going to travel through the steel of that wall. And as it travels through that steel, that's why a better coating makes it worse, because the better your coating, the better that steel's isolated from the earth, so that current wants to stay on your pipeline. So the more it stays on there, the higher you're going to pick up, the more current you're going to pick up. Your voltages are going to be where that current's going to get off your pipeline to go back to the source. That's where your voltage is going to be. So what we're trying to do is determine the locations of the voltages, where's that current getting off. That's what the model does for us. And also the magnitude, how high is it going to be when it does get off. Now, look at the illustration right here, kind of recap what I just told you, help you understand this. Now, if you look at these three phase wires, I got A, B, and C. Again, that's three phase wires, makes one circuit. I'm just going to say that each one of these is carrying 1,000 amps, okay? So they're balanced in the current, right? Each one of those is flowing 1,000 amps. Now, if you look at each one of these from phase C to your pipeline, from B and from A, they're all different distance away from the pipeline, right? And since they're a different distance away, that creates an imbalance. See, that's a distance imbalance we call right there. So they will pick up, that pipeline will pick up some induced interference because of that incomplete cancellation. If these wires were right on top of each other, in other words, if each one of these was the same distance, they would cancel each other out, and you wouldn't have any interference at all. Okay, so that's what we're looking at. We have that incomplete cancellation because of that distance right there between those phase wires. And like that's what I told you earlier, the farther apart these are from each other, the higher the interference. And that's because the farther apart they are from each other, the bigger the separation distance is going to be right here between each other. And of course, the bigger that distance is, the higher the imbalance and the more interference that you're going to have. Okay. Now, remember, when you hear us talk about induced, we're talking about these steady state conditions. Now, steady state conditions are the conditions that the power line operates at all the time. You're doing normal operating conditions. Now, don't let that term confuse you. it varies throughout the day. In other words, if you go to a power line that's feeding a plant, the load going through that wire, those phase wires, even under a steady state, is going to vary based on what the load is at that plant. If they're feeding a town, they'll vary depending on when the people are washing their clothes and watching TV or whatever they might be doing. So even though it's steady state, it does vary throughout the day on what that load's going to be. Now, when you have a pipeline and you in a power line sharing the same corridor, okay, and it's within that magnetic field, again, what you're going to have is that current, and the voltages are going to be at locations, what we call excitement points, but it's anywhere that something changes along that corridor to excite that current. Okay, that's why we call it an excitement point. It can be a change in the power lines. Your power lines can change their spacing from each other or the height above the ground. It can be a change in the geometry. Maybe you were running parallel and all of a sudden your pipeline veers off to the right or left. You have a change in geometry. You'll normally get a peak in that area. It can be changes in the pipeline material. You can change diameter, wall thickness, coating, anything like that. Those areas are where you're going to see those voltage peaks come up. Anything that will cite that corridor. Okay. Now, for any level that we call, again, we call it an excitement or any level of excitation, the strength of that magnetic field, okay, and is going to impact that induced voltage level. And again, and you'll see it change along that corridor. And all that's saying there, however strong that magnetic field is going to be how strong those voltage peaks are going to be. And when we talk about our magnetic fields, those are measured in volts per unit length, whatever length you're looking at. And so if you're picking up 10 volts per mile and you parallel for 2 miles, you're going to pick up 20 volts. Now, what the model does is tell us where is that 20 volts going to be at, because you might have 10 volts on one end and 10 volts on the other end and 0 in the middle, or some other combination. So that's why the modeling is so important. It's pretty easy to determine I've got interference. The challenge comes in determining what's the magnitude of that interference and where is that interference going to be along that pipeline. Give you a quick illustration right here. Let's just say this is 20 miles. It could be any length, but if that's a 20 mile length, and I was picking up 2 volts per mile, I'd pick up 40 volts, right? And what you'll see a lot of time, now not the exact point, but somewhere in this area here is you're going to have a peak, and somewhere in this area here you're going to have a peak. And again, it depends on a lot of things that we don't have time to go into today, but that peak could be anything from very small to very high. But if I'm picking up 40 volts, if that was my total level of induced I was picking up, I won't have more than 40 volts on there anywhere, right? Because that's what I'm picking up. But I could have 20 volts here and 20 volts here. I could have 0 volts here and 40 volts here. Again, it all depends on our terminating impedances and things of that nature. But again, that's where the modeling comes in. It tells us where those volts are and where it's going to be. Now, I can tell from looking, I'm going to have peak in this area right here, but I have to do a little bit of modeling or analysis to know how much I'm going to have. And often, if you have a long pipeline running for a long area, a lot of time your volts will be 0 throughout a lot of that pipeline. And because you got current, it's all current going through the steel, and it's not any voltage. Remember, the voltage is always where that current wants to get off pipeline, go back to the soil to get back to a source. AC is no different than DC. All current has to get back to where it came from. Okay. Now, steady state. And by the way, steady state conditions is the condition that impacts your AC corrosion. Okay, so when you're dealing with AC corrosion, we always focus on the induced steady state levels of interference. Now, what about fault conditions? Now, if I have a single what we call phase to ground fault, and what that means is this wire in this example here, this phase wire C, somewhere along that corridor shorted to ground. Okay. Now, when a phase wire shorts to ground, the impedance on that wire, the resistance in corrosion terms that we deal with in DC, but the impedance on that line drops real low, and the current is going to get real high. So remember I told you earlier, if each of those wires were carrying 1,000 amps, and all of a sudden now phase C shorts out, so it's going to pick up to 9,000 amps. So you see that big imbalance right there? So your induced level during a fault is just going to get a lot higher because of that very high current that you're throwing through right there, okay? So you'll have a much higher induced because of that higher amps. And in addition, the conductive going through the soil that I showed you earlier, we have to add that to where we're faulting as well. So that faults are very problematic because the voltage gets so high that they're the kind of conditions that can kill people. Not just shock you, not just hurt you, but they can kill you. They're the kind of conditions that can cause coating damage. They're the kind of conditions that can even in some cases cause pipeline damage. So our models, we're very careful on how we model our fault conditions and make sure we try to get the right conditions, because fault conditions are something you can't go out in the field and measure. A fault just happens when that wire shorts out or gets short circuited. So the only way to have any idea about the fault conditions is to do some type of modeling or analysis. And again, it's very, very, very important to do. This graph here is a good illustration. This is the one I showed you earlier. Now, this right here was a steady state graph. This is what I told you, right at 180 volts. Now, that was during steady, the 1,000, during steady state conditions. Now, during a fault, at this tower right here, the tower was faulted right here about the 31 kilometer mark. Now, look how much your induced went up. You're almost at 15,000 amps. You went up from 100 volts. You went up from 180 volts to 15,000 volts because of that 9,000 amps going through that wire. It made that induced get so high. Okay, but you see how the graph looks the exact same. They will. It's the same shape. They just gonna get a lot higher. This part right here, that's the conductive part. That's the part going through the soil. And of course, it's added. So you've got your induced part right here, and now you have to add all that conductive to it. So if a poor person happens to be out on a pipeline at an above ground test station right here and taking a reading when you have a fault, he's going to see over 20,000 volts, which is going to produce enough current to kill him. So that's what we're very careful for on these fault conditions. Okay, the factors that contribute to the AC interference, soil resistivity, the magnitude of the current. We've already talked about the current's a big thing. The geometry, how far apart the power line is from the pipeline, how the power line's operating. Are they balanced? Are they unbalanced? That has a big impact on the interference. Your fault currents. What's the magnitude of current when you have faults? Grounding characteristics. How well is the towers grounded, and also what kind of coatings do you have on the pipeline? All those go into, and again, all those impact the levels of AC interference that you're going to have. So that we got a little bit of background about the AC interference. Let's talk a little bit about how we investigate it, how we go about looking at it. I will tell you that when you're going to do an interference study, regardless of how you do it, you make sure you follow a good plan, and you document your plan, and you document what you do. And we'll go through each of these right here, but I'll give you a kind of a list right here. And this is typical that we'll break it down. There are some exceptions to that from time to time, but typically we'll break it down in information gathering. We'll come up with a plan on what we're going to do. We'll select the tools, go out and do the investigation, analyze the data, come up with a solution, and verify. So let's talk about each of those just a little bit. Gathering information. Now, this is usually the one, it's the most important step in your interference analysis. Because whether you're doing modeling or what you're doing, if you do that off of bad data or bad information, you're not going to have a good model. And I've seen a lot of models get produced and not really be very accurate tools. So information gathering is key. You want to make sure that you get the right information on the power lines and on the pipelines and soil resistivity, everything you're gathering, because when you collect that information and you go back to actually do your analysis or build your models, it's very important that you get the right information in there. So we're going to look at the physical location of the pipelines, the transmission lines. That's where we're going to measure or make sure we get a good idea of the spacing of the transmission lines, the heights above ground, any changes in the pipeline characteristics. All that's very critical, because if I've got a pipeline running through here and I'm in a corridor, at this station right here, that pipeline, 5 years ago, they had to do a repair of that pipeline. So all this pipeline here, this 500 feet's got a brand new coating than the other pipeline. That's going to be an excitement point. Okay. Now, if I don't catch that, put that in my model won't catch that excitement point, but it's going to be there in the real world. So it's very important that when you're out there getting information, that you try to gather everything you can to make your models as accurate as they can be. Okay. I'm sorry, one more thing. When you gather information, just two types of information that we gather. One is we request information from others. Now, when I was still working, most of my clients were pipeline companies. I did a few jobs where I worked for the power company, but most of the time I'm working for the pipeline company. So we have to request information from the power line company. Okay, sometimes you have to request it from other pipeline companies, but we'll go out with data requests and we'll request information. That's awful. The slowest part in the process is getting information from others. Quite often you have to wait a very long time. More and more, you're starting to see them charge a significant amounts of money to give you some of this information. So there is both a time and a schedule cost involved when you get that information. So make sure you get that started early in the process. Don't wait till you don't go out and do all your field work and do everything, and then the last minute start requesting information will really hold you up. The other information we get from the field data, and we'll talk about field surveys here in just a couple of slides. So once you gather the data, you come up with a plan, okay? So part of the data is, of course, you've identified the area you're just going to investigate. Now, a lot of ways to do that. A lot of time we'll do it with GIS mapping, like we have in the PRCI model. You can do it with Google Earth mapping. There's a lot of ways people go in there and they'll identify the area, and they'll kind of come up first with when and where we're going to start the investigation, what area we're going to look at. And then once you do that, you got to make decisions on what kind of equipment you're going to use and what type of measurements you're going to do. And this right here is key, because a lot of times the people out there collecting that data aren't going to be the same people that are in the office building the model. So you need to make sure that there's a good data dictionary and the data is being collected in a way and stored in a way that the people in the field know what it is and the people in the office know what it is and can understand it. Okay. So you got to come up with a plan to make sure all that's going to happen and it's going to happen smoothly. Then you select the proper tools. What kind of tools you're going to use. For all your data collection, your data storage. And if you're measuring heights, you have the right kind of range finders and the right kind of source sensitivity tools. Make sure you've got the right tools to do what you're going to do. During this time too, we'll also determine how you're going to analyze it. Are you going to model it? If you're going to model it, what kind of model you're going to use, how you're going to build that model, all that goes into selecting the proper tools. Then once you've got that, you do the investigation. You run your model, do your analysis, and the model will give you information, will give you graphs and all kind of information about your steady state levels, your induced levels, your fault conditions, your coating stress voltages. And of course, you get all the data, you analyze the data and determine if you have a problem. Like I told you, I can look at your corridor and tell you got interference or not. I can answer that in 5 minutes. But what I can't tell you is what that's going to look like until I analyze that data. Then if the data suggests we're going to have any safety issues or pipeline integrity issues, then we got to come up with a solution to lower down that voltage where it's not a problem. And of course, to do that, we got to consider the environment we're in, the terrain. I don't talk about mitigation design in this webinar, so I don't have time. But get very, very. The mitigation design is highly dependent on the environment, the terrain, things of that nature. Okay, and then we'll evaluate the cost and pick the best way to go and go from there. Don't forget this right here. Once you've installed that mitigation, always make sure you verify the solution performance. Because a lot of times it's not uncommon that your model said one thing, you did the mitigation, and when you install that and go check it, it's not what you thought it was going to be. And there's a lot of reasons that can cause that. But again, make sure you don't forget that step to verify your solution performance. Okay. Now, again, I've already talked about collecting the data. Just remember, collecting data from others, like I mentioned that, a lot of time that's going to be the slowest effort that you're going to have in the process. So make sure you start that early on and not too late. What kind of data we ask for? Current loading. Remember I told you current was a key thing, right? So we want to get the current loading from the power company. I can't go out in the field and measure current in their phase wires. Well, you can in certain ways, but not anything accurate. So we like to get that from the power company. What are you loading those phase wires at for current? Is there any imbalance? Other words, they don't always have more every phase wire is carrying the same current. A lot of times, especially with some of the older systems, they'll tell you, yeah, this one's you got a certain imbalance. This one's a little bit less current, and so that's good enough. Because again, that impacts your level of interference pretty high. You're kind of loading. Remember, I told you that steady state is based on the demand. So a lot of times they'll have their peak load, which means, of course, the worst demand. Then they'll have the winter loads and their summer loading. Now, when I model for safety, I'm going to model the highest load there is, because I got to make sure that pipeline is safe all the time. So I always want to know what the peak loading is, and I'm going to model that peak loading for all of my safety considerations. Okay. Now, when I'm modeling for things like AC corrosion, then I'm going to look at more of a steady state, and it could be the winter load or the summer, whichever is the highest. But I'm not going to do my corrosion off of peak load. Those peak loads don't last that long. They're there maybe a short time during the day, so they're not there all the time. So, you need to get that from the power company. And of course, on the fault currents, you need to get what the fault current's going to be when they have faults. Phase wire data, anything they can give you about the wires. When you look at this right here, now each of these is a circuit. Remember, 3 phase wires is a circuit. So when you look at a corridor and you've got multiple circuits, then how those wires are phased, we call that phasing. And that's the angle degrees they are apart on the current flow. And that has a big impact on the cancellation. So when you got multiple circuits, it's very important to make sure that you get the phasing data from the power companies, because that can have a big impact on your level of interference. If you don't get that, then again, we'll do a worst case by making the phasing identical. That's always going to be your worst case. That way you have no cancellation. It's best to get that from the power company. If you have one circuit out there, the phasing doesn't matter. In other words, if you don't know what it is, because they're 120 degrees apart, that's how they do their wires, their circuits. But it don't matter which one's 120, which one's 0, and which one's negative 120 if you've only got one circuit that's out there. Okay. Pipeline parameters: diameter, wall thickness, the burial depth, the coating. Those are key things that come into play there. Normally, we'll use the pipe burial depth down to the center of the pipe, and we'll use that for our soil resistivity measurements and where the pipe's at. Coating is, again, the biggest impact on, like I told you earlier, and the coating is the most subjective. It's the biggest impact, but it's the one that we don't have an exact thing on what it is. It's going to vary based on soil resistivity. It's going to vary based on the coating and how effective the coating is, but it has a big impact. But when we do our analysis, we have to come up with a value for that coating resistance to use it in our models. This right here is just one example. This right here is the AGA and the NACE manual on AC's got it in there as well. But a very common way to do it is to do it based on the soil resistivity. And you determine whether you've got an excellent coating, a good coating, or a fair coating. And then you multiply it by a number, 5.2 or 0.5, and you multiply the soil resistivity in ohms per meter. And that'll give you what value that we'll typically use. Now, right here is what the guidelines they use for whether it's excellent, good, or fair. You can see those right there. Excellent is less than 5 years old with no change in CP current. Good is usually 5 to 15 with a small change in CP current, and fair is where CP demand has increased, pretty much from the original design. All you do then, you take it. If it's excellent, if soil resistivity is 25 ohm meters, you multiply it by 5, and so now this is in 1,000 ohms per square feet. In this case, it'd be 125,000 ohms per square feet would be your cutting resistance. Again, big impact that has on your model, and you'll have several of those throughout a model. If I've got 4 miles of pipeline, I might have different soil resistivity 5 or 6 times along that pipeline. And each of those will be excitement points that will affect that. So you have to watch that real close. Okay. Field surveys. So we request that from us. We also go out and we do field surveys. Now, main thing we do out in the field is we're going to collect all the data we can. We're going to measure the wire heights, and we'll get GPS readings of all the above ground components and where the towers are and anything else that might be of interest to us out there. And we'll collect all that data and bring it back in to the office for our modeling. And even if we get some of that data from the power company or the pipeline company, we'll use our field survey to kind of verify the data that we get. Okay. So again, very important that we make sure our data is good, accurate data, because again, if it's not, our model's only going to be as good as that data that goes in there. Okay. Now, during the field survey, we're looking for all those areas where we expect voltage peaks. Like I told you, we know what area they're going to be in, and we just don't know how much they're going to be. So, we're looking for anywhere that the pipeline geometry with the power line changes, or anywhere where the separation between them changes, or where the power lines themselves change. That's a transposition, where their spacing or change. Anywhere that we might cross under a power line. And anywhere the pipeline characteristics might change. We're going to look in those areas as well, okay? So when you're doing that field survey, we're going to identify all those, and we're going to GPS them again, and that way when we do our model should show a peak there. We don't know what it's going to be, but we know it should show an uptick in the volts. And if it doesn't, then we know something's wrong with our model. Because if I was out there in the field and all of a sudden the pipeline turned and went that way, the power line was going this way, I'm going to get a peak in here. If I don't get a peak in there in my model, then I know something's wrong with my model. Okay. Soil resistivity. I'm not going to spend a lot of time on that today, but make sure you got the right tools, and we go out and do our soil resistivity. The big thing I want you to remember on this, if you look at the depth right here, we collect a lot deeper soil resistivity readings than we do for CP design. Typically, we'll go at least 100-foot pin spacing, because that deep layer of soil has a big impact on the strength of that magnetic field. So make sure you do your soil resistivity measurements, that you do that deep layer. And we normally use the Wiener 4-point method, just like we do with CP design. We'll just space the pins a lot farther apart. Okay? Again, and normally we'll do it at any above ground apparatus. We'll do it anywhere where we see something that changes the environment. And outside that, we'll do it at least every a mile, 2.5 miles a mile, just to get a good soil resistivity. Basically, what we want to do is wind up with a graph like this of what the average soil resistivity is along that route. Okay. So predicting it, that's a complex matter. It requires some what I call sophisticated mathematics with complex numbers. Again, and most time we'll do it with our specialized software and take all that out. But you see, some of these corridors can get pretty complex. Okay. So using the computer program. Now, several programs out there, the PRCI program, the HD AC power tool programs out there, and there's others. And but they're very good to model right away. But again, I want to really reinforce those models are as good as the data that you put in there to model that with. So you got to make sure you get the right power line data, the right spacing, the right geometry, the right pipeline data, and to build an accurate model. Okay. Now, these are what we typically model. Our steady state induced levels. Now, we use that mainly for our AC corrosion, and we use that for our steady state voltage levels. That 15-volt limit by NACE, that's a steady state level. So we use steady state for safety and for corrosion. The potentials under phase to ground fault. Okay. Now, again, those we use that for safety considerations when a fault happens. Of course, potentials to remote earth, our step potentials and our touch potentials for our safety issues. So typically any model you do, you're going to come out with each of these, and any of them that are problematic, any of them that exceed the levels that we've established, we have to mitigate that. And you know, in some case, sometimes AC corrosion will drive our mitigation level. Sometimes the fault condition will drive our mitigation level. So it'll be different things that they'll drive that. Here's just one typical graph right here. I don't spend much time on these, but you know, when you do a model, you get this. So this right here is about a 5 mile, 60,000 foot model right here. 2 pipelines, a 40 and a 36 inch. So you see the 36 inch is in good shape, no problem. Now right here's the NACE allowable 15 volts. Is right here's your 15 volt limit right here. So you can see all this area here exceeds that NACE limit. So what you do in the model, when we built that and run the model, then you'd go in and apply mitigation to get that down below the 15 volt limit. Here's the same model after we applied mitigation to it, okay? So you see now everything's below that 15 volt limit. Now again, when you build it, you got to verify that performance, but that's what the model expects you to do. Here's the same thing during a fault. Now with a fault, it's not a 15 volt limit. We use the IEEE, what we call the allowable touch or step potential. That's another calculation we do. In this case, it's about 990 volts. See right there. But again, you can see everywhere up here, you exceed that. So again, you have to mitigate it to get down to where you're in those safety limits. Okay. So that, you know, modeling is what we use to help us see that and apply the mitigation and make sure that we think we're going to be both safe and we're going to meet all the pipeline integrity issues that are out there. Here's just another version of a model. Again, this blue line right here is your voltage. This red line here is your current. And you see what I was telling you about? When your current's highest, your voltage is lowest. You know, because you're either flooring current or you got voltage, one or the other. Now here's your AC current density you use for your AC corrosion. That's that green line right here. That's your AC current density. So again, so your model will check each of those areas for you. Okay. Now remember, if a pipeline lies parallel, that's when you have full coupling. When you're straight beside each other, that's the worst case for induced. That's full coupling. And as you start getting an angle, as you get away from full parallel, you'll still have interference, but you'll get less and less. Now, when you get to a perpendicular crossing, in other words, if the pipeline is cutting straight across that corridor, then you won't have any induced interference at all. Okay. Now we'll rank these things based on the threat, and these tables here, you can just kind of see how we rank them. Anything that's within 100 feet between the pipeline and the power line, we call that a high level. And 100 to 500 medium and so forth. You can see our tables here. We'll rank them based on current. Anything more than 1,000 amps, we call that very high. 500 to 1,000 high. You see how we rank those. And of course, we have it for source resistivity. We have it for co-location length and our crossing angle. You see anything between 0, that's perpendicular, parallel, and 30 is high. 30 to 60 is medium. Anything greater than 60 degrees is a very low chance of picking up any interference. So you can look at these threat assessment tables and kind of get an idea of how high is my threshold level, and it give you an idea of whether you're going to have a problem with AC interference. Again, here's just some things to recap what we said. Anytime the center pipeline is within 1,000 foot of a power line, make sure you want to model that. You want to analyze that. Closer the pipeline gets, the higher the risk. Anytime your angle gets less than 90, you're going to have that. Angles less than 30 are going to get a higher and higher risk. Okay. Anytime you're co-located for more than 1,000 feet or so, you pay attention. Anytime you're more than 5,000 feet, we call that a high risk. All right. Now, one thing I want to say, we'll get ready to close out here, is there's a lot of disagreements and a lot of discussion out there between the value of computer modeling compared to field analysis and design. Now, I will tell you, both methods work if done properly, and both of them require good field data, and both methods require good verification to make sure they work. Big difference is, if you're using field data, if you go out to a test station and you measure your AC volts, and let's just say you measure 10 volts, And so you're going to use that 10 volts to say you're okay. And let's say you measure that 10 volts at 10 o'clock this morning. You go back out there at 3 o'clock this afternoon, that 10 volts might be 20 volts. It might be 4. You don't know. Remember, I told you the volts is based on the current, and the current varies over time, depending on the loads that are downstream. So if you're going to try to do a analysis of AC without modeling, you want to do it based off of field work. You have to put data loggers out there and collect data over a period of time. I recommend you ought to collect it for anywhere from a week to a month, to make sure you get the right data. But if you collect that data over a period of time, then you can use that, but you can't just go measure it and do it based off that, okay? If you go to that, you need to model. This right here is the other big thing about the field work. Field design does not cover fault conditions. Unless you're out there during a fault, you're not going to have a clue. So even if you do a field analysis for your steady state, you have to do fault conditions have to be based on modeling. Okay. All right, Nick.
Awesome. Thank you, David. Great, great information here. So yeah, I know we've only got a few minutes left in the presentation. I just want to highlight 2 more items from our side. So, if you did like hearing from David today, good news. We have a lot of upcoming events where David will be front and center. So wide variety of training upcoming from David here in the next 3 months. So we got some of those listed on the left-hand side, and you can see those more on our website. Next slide, David. And we did just get a question about trying the software. So if you are a PRCI member today, I mean, good news. The kind of baseline software is free. And so we can, go ahead and fill out the poll if you are interested in seeing that. If you are a PRCI member, or if you're not a PRCI member and you just want to get on the software as well, go ahead and fill that out too. Regardless, we have about 2 minutes left, and we do have these questions. And for everybody else, we do have a list of the questions, and we will follow up via email just to make sure that you've got your questions covered. So the one question I think we probably do have time for, David, is how do you estimate AC current density on the pipeline to establish the likelihood of AC corrosion?
Okay, there's 2 ways to get your AC current density. Of course, one way is put what we call an AC coupon, and an AC coupon's a metallic disc of the size of it. You put it in the ground, you bury it, and you measure the AC current going through it. And of course, since you know the size, you can convert that to an AC current density. So that's one method we use quite often. There's another method you can use where you actually calculate it, and you calculate it based on the AC volts that you have in there. And normally we assume a 1 centimeter square holiday, which that's usually a worst case on the level of AC corrosion. And we can actually calculate it using a modified version of Ohm's law, and we'll calculate what the AC current density is. So 2, it can be calculated or it can be measured.
Awesome. Okay, and maybe we'll do one more, David, and then again, for everyone else, please know that we will follow up via email for your other questions. Is our only concern when a power line crosses a pipeline the fault current and not the induced current?
Yes. If you have a pipeline running this way and you got a power line right here, now if that pipeline turns and goes perpendicular across that line, the induced level of interference will be 0. There'll be no coupling at all if you cross perpendicular. But as you start crossing at an angle, remember that chart I just showed you? Once you start going at an angle, it's going to start picking up more and more. So anything between perpendicular and 30, you don't pick up much to worry about. Once you start getting anything of 30 or less, then you want to model that.
Awesome.
But you said it right. If you do cross perpendicular, you still got to check for faults. If that tower faulted, you still got to check that conductive level of interference.
Great question, and thank you, David. Okay, well, I know we are at time for the webinar, so I just wanted to say thank you again to everyone that did attend, and we hope you found this information useful. For the folks that didn't get their questions answered, we will follow up separately from here. But I'd like to thank Gary, I'd like to thank David, and I'd like to thank all of you for your time today. Have a good day.
Again.